Hello everyone, welcome to topic 5.7, Introduction to Reaction Mechanisms. By the end of this, you should be able to identify the components of a reaction mechanism. We are going to dive a little bit deeper into this. We started out with it earlier in this unit. We're going to dive a little bit deeper into it and look at it in more detail, and we're going to continue to peel back layers as we proceed through the rest of this unit. Okay, so let's get started. Many reactions do not occur in a single step in which reactants are directly converted to products. We've seen that. In reactions involving multiple steps, the overall reaction occurs in a series of reactions or elementary reactions or steps that occur in sequence. So there's an order. Each of those steps is called an elementary reaction. When the elementary reactions are combined, they give the overall reaction. So as an example, the conversion of ozone to oxygen occurs in two steps as shown here. The elementary steps can be combined where we cancel out things that are common on both sides of the arrow, like you do in net ionic equations, to give the overall reaction. Please note that the combination of elementary steps must match the overall balanced equation in order to be a valid mechanism. So if these two steps did not combine to the actual reaction equation, like what we would normally write, it is not considered a valid mechanism. Like, that is not how that reaction can proceed because it doesn't match what the overall reaction is. So in the example above, we see that oxygen, the atom, is an intermediate. It appears first as a product in the first step and then is consumed in the second step. And that is the definition of an intermediate, where it is only present while their reaction is occurring. So it is first produced and then consumed in a subsequent step. So this does not appear as a reactant or a product in the overall reaction, so it should cancel out. When the mechanism is proposed as a possible pathway for a reaction to occur, obtaining evidence of the presence of an intermediate can either support or refute the proposed mechanism. So while chemists who are doing research are like checking to see how these mechanisms go, if they propose that an intermediate exists in their mechanism, they're going to run tests on the reaction as it goes to see if that intermediate does pop up, even if it is used periodically. Okay, so the conversion of ozone to oxygen can be sped up by chlorine-free radicals. In this case, chlorine-free radicals are considered a catalyst of the reaction, and the chlorine oxide molecule is created as an intermediate. A catalyst will appear first as a reactant in the rate determining step, because it's going to be the one that controls how fast the reaction goes, but then it is also reproduced or appears as a product in a later step. So it is first used, so it'll be consumed first, and then it's reproduced as the reaction finishes later. So a catalyst also does not appear as a reactant or a product in the overall reaction. So to summarize a little bit, intermediates are produced and then they are consumed, whereas catalysts are consumed and then produced again. And these are done in different elementary reactions. Now, you can produce an intermediate when you use a catalyst. However, the production and being produced and being consumed for an intermediate, those are going to be two separate elementary reactions. Same for a catalyst. It'll be consumed in one and reproduced in a later elementary reaction. So let's look at how we can use these concepts in application. So we are going to write the reaction represented by the mechanism shown below. Obtain the overall reaction by combining the steps and eliminating catalysts and intermediates. So when we look at the arrow, we're going to cancel out anything that is the same on both sides, which happens to be that oxygen atom. And we see there's nothing else that is on both sides exactly the same. So we are going to write our overall reaction as 2N2O yields 2N2, and they're all gas. plus oxygen gas. So this is similar to how you would combine redox reactions, where you have the two half reactions and you combine them and you cancel things that are on both sides, or when we looked at net ionic equations and we canceled out spectator ions. So they have to be the exact same on both sides of the reaction. So identify the catalyst as a species present in the reactant in the first step and product in the second step. Well, we don't see anything that is a reactant in step 1, and then we canceled out in step 2 on the product side. So there is no catalyst. So no catalyst. And then identify the intermediate. Well, the intermediate is the one that is first produced and then consumed again. So that would be oxygen atom is the intermediate in this reaction. Okay, now looking at this one, which mechanism below is a valid mechanism for the reaction shown above? Explain your answer. Well, the easiest way to approach this is to see do either one of these add to the overall reaction? So we're going to look at mechanism 1, and we're going to cancel out what's the same on both sides of the reaction. So this is on both sides of the arrow, and we look at everything else and we don't see anything else. So now we're going to add it together, and so we should see 3NO from these, and that's a gas, plus oxygen atom yields the oxygen atom actually cancels out. My apologies. So that is going to yield 2 nitrogen dioxide molecules. And does that match? We're going to look, does that match? And no, it does not match. So we're going to check mechanism 2. So please pause the video and on your own, check mechanism 2. Okay, so checking your work, you should see this equation when you cancel the things out that are on the same on both sides of the equation. And so we see that it does indeed match the overall equation. And so we would say that mechanism 2 is valid because it sums to the overall reaction. Okay, so using these concepts, you're going to apply them to the UDOs. Please check your work as you go, and thank you for tuning in.